I want to start today with a bit of a pop quiz. And so try to answer, I'm not going to collect this or anything. Try to answer the following questions, ideally without referencing the notes. If you need to, then crack them open, and also feel free, try to answer it on your own, but if you want to discuss with your neighbors, that's fine too. Very important. Here's the question. One of the graphs to the right is y equals sine of x. Which one? One of them is y equals cosine of x. Which one? And then finally, what are the other two? Let's try to move these so that you can actually see the blocks. Good enough? All right. All right, so take a moment. Think about these. I'll give you like a minute or so to think quietly on it. Maybe you write down what you think the answers ought to be. Alright, if you need to now, then crack open your notes and see if you need those to get the answer. Or if you already have the answer, crack them open and see if you can use that to conform. I see you already have them open.
I just do that.
You're good. Take like some fraction of the remaining minute I want to give on this. Talk to those around you, see if you all agree. Let's hear it. So the first question is, which one is sine of x? Which one is sine of x?
C.
Do I hear a C? Do I hear a second? All right, yeah, looks right. Why C? What was your thought process?
Goes through 1, 0, 0, and comes out positive.
Nice. Starts at 0, 0, but it increases right there, which is what you know sine should do. Which one's cosine? Sure.
D.
I hear a D. Do I hear a second? Cool. Why D?
Because it versus point 0, 1.
Nice. Cosine of 0 is 1. All right, so there are two options that haven't been used. What are they? What does A seem to be? Sure.
Is it the inverse of cosine?
Which inverse do you mean?
Like to the negative power.
I don't think it's to the negative power. So imagine what negative power would mean. So like that?
No, or the
Like that?
Top of the cosine where you wrote it the first time.
Ooh.
So is that called the inverse?
Yeah, so there's a function that we'll study called inverse cosine. And it's literally the inverse function to cosine. So it's like what you get if you swap the role of x and y. Does that graph of A look like the graph of D, but with x values and y values swapped? so I think it's not that. Inverse cosine is something we will study. This is something simpler than that. And there is a way to describe it using the word inverse. How does A seem to compare with cosine of x? Like what symmetry of the plane relates them?
Reflected over the x-axis.
Reflected over the x-axis. What manipulation of functions corresponds to that reflection? Not negative x, just negative cosine of x, though. So to go from here to there, all the y values just become negative. That corresponds to sticking a negative sign in front of the function. That seem fair enough? All right, with that in mind, what about b? Sean?
Negative sin of x.
I hear a negative sine of x. Let's see if we can conform that. So negative sine of x should mean you start with the graph of sine of x, and you reflect it over the x-axis. So this point will go like down there. So something like that. I agree with B. Cool. Nice. Folks feel all right about this? Groovy. So now that we have just that recalled, let's see what we can do. So you said once like increasing during the decision that C should be signed. It's increasing at 0, and it goes through 0, 0. So let's think about notions like increasing and decreasing. We have graphs of the trig functions. They're also in the notes, so now we'll move to the notes. Let's try to decide whether trig functions are increasing and decreasing based on that. So I think the way to do this is let's just start writing down some intervals. So there's the graph of sine of x. At x equals 0, does it seem to be increasing or decreasing? Cool. How far to the right could I keep going and have it continue to be increasing? Pi over 2. Cool, yeah. You could get to there, and then it would turn around. So it's increasing until pi over 2. And let's find the left endpoint. How far to the left can I go and still have it be an increasing function? And in fact, that's something that we've kind of seen before. Since sine of x is, oh, I'm off the screen completely. Since sine of x is odd, the intervals of increase and decrease should have a nice symmetry. So that must mean at pi over 2, it changes to decreasing. And by looking at the graph of sine of x, if you start at pi over 2 and start going this way, how far to the right can you go and still have it be decreasing? When does it turn around? 3 pi over 2? Right. There's a turning point right here. And let's do like one more increasing and one more decreasing. So at 3 pi over 2, it starts increasing again. How long do you think it'll keep increasing? When do you think it'll turn around again? I guess at that point we're off the edge of the graph provided. So let's see what we can read off of like a Desmos graph. Don't want these yet. So it increases until pi over 2, then it decreases until 3 pi over 2, and then it increases again until 5 pi over 2. And maybe there's a pattern you're noticing here. 5 pi over 2. So what's your guess based on that pattern? Well, you couldn't see that. So 5 pi over 2 is the next taunting point. How long do you think it'll be until it taunts again? Anyone notice a pattern so far? It taunted at negative pi over 2, 3 pi over 2, 5 pi over 2. Difference of a whole pi between them. So I guess the next one will be like 7 pi over 2. And I think that's as far as all right. And now let's just confirm that intuition by checking out the graph. There's 5 pi over 2, 7 pi over 2, 9 pi over 2. Yeah. It looks like every time you go right by pi, you get to another taunting point, starting at pi over 2. Groovy. So, there's a property that you also see with these trig functions. They kind of just do the same thing over and over again, which I guess makes sense because if you rotate by an angle, once you get all the way around the circle, you'll just do the same thing again. So all of the trig functions should have like a repetitiveness property. They should do the same thing over and over again. The technical word I'll say for that is periodic. A function is periodic if there's a non-zero number p, called the period, which satisfies that f of x plus p is equal to f of x. And in fact, the restriction is p is the period if it's the smallest positive number that satisfies that. And I want to pick the smallest positive number because, right, if a function has period p, then if you add p twice, the function will still be the same. So I want to say the period is the smallest number that does that. So let's look at the graph of cosine and try to figure out its period. So, in doing so, that QR code takes you to exactly this graph. So there's the graph of cosine of x and cosine of x plus p. I want to pick the smallest p so that those two things will lie directly on top of each other. Does it look like p equals 1 walks? No. So, I guess let's just start moving it forward and seeing how long until it does line on top of itself. Not good yet, not good yet. Well, it's starting to look pretty good now, right? But do you think 6.27 is like exactly the period? Seems unlikely, and in fact, you can see it's a little bit off. But I think this gives us a pretty good idea. What's a number you can think of that's like trigonometry related? That's pretty close to 6.27. 2 pi. Right, if pi is 3.14, I guess 2 pi is about 6.28. So let's see. What if we tried to take p equal to 2 pi? That look pretty close to dead on now? All right, cool. So, by looking at this graph, the cosine of x sure seems to be 2 times pi. And now maybe we'll just think if that makes sense. What sort of angle does 2 pi correspond to? Say louder? 360. 360 degrees. So, cosine of x records the x value, right? So it starts at 1, and you go all the way around the circle when you go around by 2 pi. If I just keep on increasing the angle, do I do the same thing as if I ignore that plus 2 pi? Yeah, right? And extrapolar evolution doesn't affect cosine. Cool. Intuition. What do you think the period of sine should be? Let's see, sine is like the y value? How far around the circle do you have to go before the y values start doing the exact same thing again. Oh, I don't know. There's the graph of sine right there. If I wanted to shift this thing to the left by some amount, I'd need to find a point over here that looks the exact same as that point that I could shift to the left. So by looking at those 2 points, how far to the left do you think I should shift sine of x to get back to sine of x? Seems reasonable. Let's just double check using the computer-generated graph. If I graph sine of x and sine of x plus 2 pi, remember p is 2 pi and that Desmos Interactive right now. Yeah, I'd say that looks pretty good. So period of sine, also 2 pi. Nice. All right. So, let's see, based on the previous page, there's the graph of cosine of x and the graph of sine of x. And here's one more observation I want to make right here. Do those two graphs look pretty similar to each other? Right? Yeah, the sine of x is cosine of x just moved over a little bit. I don't need one. But let's try to figure out why. So here's the question. So cosine of x is just a shift of sine of x. So let's look at sine of x and decide how far to the left we need to shift it to get to cosine of x. And I don't know. Let's use that point. There's the point 0, 1. So that's like a peak of cosine. So looking at the graph of sine of x, is there a peak that's just a little bit to the right of that we could take advantage of? What are the coordinates of that peak?
Zero.
Sine of x, not cosine of x. Pi over 2, comma 1. There's a peak. So let's see, if I take that peak and just shift it to the right until it lands on 1, 0, will that give me the exact same graph as cosine? Cool, so if I start with sine of x, if I shift left by some amount, I'll get cosine of x. And it looks like, how far left do I need to shift it? I guess pi over 2? Oh, neat. Well, I know what shifting left by pi over 2 does to a function, right? That corresponds to adding pi over 2 to the x value, to the x inside of the function. So cosine of x is the same as sine of x plus pi over 2. And that's a useful fact sometimes. That's a fact that says if you know cosine of some input, then you also know sine of some other input. It's just that same input, but added to pi over 2. Feel pretty good? Nice. Amplitude. So, periodic functions have an associated quantity called amplitude, which you should think of as being like how high are the peaks and how deep are the valleys. We use the following formula to get them. The amplitude is given by computing the maximum value that a function takes, periodic function takes, minus the minimum value that periodic function takes, and then dividing that by 2. Because right, if you go all the way from the peak to the valley, that's like we're calling double the depth of that valley. You should measure from 0. So let's try to determine the amplitude of sine and cosine, and let's start with cosine. So there's the graph of cosine up there. Let's compute the amplitude. So the amplitude is 1/2. What's the maximum value cosine takes? Take a look at the graph of cosine at the top of the page. How big does it get? 1. what's the minimum value cosine takes? So the amplitude of cosine is is 1. It'll be 1/2 times 1 plus 1 theta. Similarly, the sine has the exact same amplitude. The amplitude of sine is also 1. So whenever you have a periodic function, you can compute this amplitude. And in fact, a general sinusoidal function is some function of this form, a times sine of a number times x plus a number, close parentheses, plus a number. So if you have something that's the result of sine of x or cosine of x after some transformation, it turns out the period will be 2 pi divided by the absolute value of omega, and the amplitude is given by the absolute value of a. And notice those absolute value errors. We'll figure out why those should happen on the next page. But in the meantime, let's use these formulas, compute the sine and cosine of some functions, then we'll look at graphs and see if these things seem to agree. So here's what I'll have you do. Use those formulas. Compute for me the period and amplitude of the functions below. And maybe I'll give you some space. Does anyone feel like they don't understand what I'm asking them to do and would like me to walk one of them in advance? Okay, cool. I'll talk through the first. So the period of a sinusoidal function is 2 pi divided by whatever omega is. Omega is next to the x. So in this case, there's the omega. It's 3. So the period will be 2 pi divided by absolute value of 3. And now we'll try to simplify. What's the absolute value of 3? After you remove that absolute value, is there any other simplification or canceling to do? So the period seems to be 2 pi over 3. We can get an approximation if we wanted to. That feel pretty all right? The amplitude is given by the thing multiplied in front. So in this case, the a is 4. So the amplitude is just the absolute value of 4, also known as 4. Think you can read that off for the remaining ones real quick? Nice. So go ahead and do that. Be careful with the absolute value bars. I am going to pull up some graphs. Are you feeling pretty good? Do people want more time to do this arithmetic before we discuss this graphically? Cool. So, yeah, let's start here. So let's see, we got a period of 2 pi over 3, amplitude of 4 for this first one. And let's try to figure out if that's correct. By looking at this graph, maybe I'll highlight some points. what seems to be the maximum value of this blue periodic function? 2. What's the minimum? -5. So the amplitude should be 3 minus 5. So that's 8 divided by 4. Yeah, that's 4. That works out well. The period is how far to the left you need to shift this thing to have it get back to itself. So it looks like the period is whatever the distance is between those two inputs. And I guess, well, we could compute that. See if we get something that's close enough to the 2 pi over 3 that we predict. All right, my memory is very bad, so I have to have everything open at the same time. About 1.43 minus negative 0.667 is about 2.1. So that means the period should be close to 2.1, but we computed the period exactly. We got it to be 2 pi over 3. That agree close enough? Nice. So I think I believe that. All right, this next one. What did you get the period to be? I hear a 2. Do I hear a second?
I have 2.
Excellent. What about the amplitude?
3.
Nice. Did anyone say the amplitude was -3? Cool. You all remember the absolute value bars. And again, let's see if that agrees with the graph. So there's this next function. Hopefully I wrote it down correctly. The period is like the distance between two consecutive peaks. Does that period seem to be 2? Nice. The amplitude is half of the distance between the max and the min. You said the amplitude is 3, so I guess that means the difference between max and min should be 6. Does that hold up? Nice. All right, now let's just go left to right and read off the rest. Period is still 2. So maybe you notice something. Do those numbers have absolutely anything to do with the period or amplitude? I guess that makes sense. That +6 is just going to take the whole graph and move it to the left or right by a little bit. That doesn't affect the period. It just affects, I guess, where the period starts. That 10 just shifts it up. Amplitude.
2.
Cool. Last one, period.
Pi over 2.
I hear a pi over 2. Do I hear a second? Nice. Amplitude. 1, not -1. The amplitude is always positive. Well, I guess, unless it's 0, but if the amplitude is 0, you have, I guess, a constant function. So you shouldn't be thinking of it as a trig function anyway. It's a line. Groovy. We feel pretty okay right now? So here's all the stuff you can do with, well, a bunch of stuff you can do by just thinking about graphs of trig functions. You can think about their period and amplitude. Their amplitude is how tall the waves are. The period is the distance between these peaks. But there are some other trig functions, right? Right, there's tangent, cotangent, secant, and cosecant. Hopefully I haven't said them in the exact same order as they are on the page. I might have. If I did, it wasn't intentional. Let's try to figure out which of these are which by thinking about what secant, cosecant, cotangent, and tangent are. So, here's the way I'll propose thinking about this. Let's try to find the vertical asymptotes and maybe also like x-intercepts or y-intercepts for things like tangent and cotangent. So maybe I'll talk through some analysis for tangent. Then I'll have you all talk through some analysis for the remaining functions. Then we'll come together and see which of these graphs is which. So tangent is sine over cosine. There's like a list of things to do. I asked for the vertical asymptotes, the intercepts, the x-intercepts and the y-intercepts. Guess we can do them in any order. Should we do vertical asymptotes first? X-intercepts first? Y-intercept first? The only preference I heard was y. It's okay that this particular vote had a very low turnout. There's a vote tomorrow that's maybe more important. So, how do you find the y-intercept? Of anything. Plug in 0 for x. So that means I need to compute sine of 0 divided by cosine of 0, or just tangent of 0 directly. Are those numbers that you just know? Yes. What's the sine of 0?
0.
Cosine of 0?
1.
All right. Alternately, how many people just have tangent of 0 memorized? That's also perfectly reasonable to do. Tangent of 0, also 0. All right, so the y-intercept should be at 0, 0. So let's think about it that way. So maybe for the sake of having convenience reference names, which of the options provided can I now eliminate? C and D, I guess. Those ones have either no y-intercept or just the long y-intercept. The y-intercept is at 0, 0. That point goes through 0, 0. I guess this one fails as well. That's right. So, I guess we have enough information. Let's see if everything else checks out correctly now. X-intercepts. I guess this is the opposite order than I give instructions to find them. How do you find the x-intercepts of a function? Plug in 0 for y. So that means sine x over cosine x equals 0 is what I need. Well, that looks like an equation that maybe takes a little bit of effort to solve. What seems like a good first step? Yeah, there's division, and that's annoying. There doesn't have to be division. I can multiply both sides by cosine of x. Multiplying 0 by cosine of x just results in 0. So I just get sine of x equals 0. And maybe here I'll propose two different ways of reading off some solutions to this. Can we read this just off of the unit circle? Let's do that first. Take out your copy of the unit circle. This is why I had to excise it from your notes. So, can you give me an angle whose sine is 0 in radians, because these graphs are out radians. Let's see, sine is the y value. Do you see a y value of 0 somewhere on the unit circle?
0% or not 0%, 0 or 180.
0, or I'm going to walk in radians because these graphs are in radians. So 0 and pi seem to do. Is there another one where sine is 0? Well, I guess maybe it's not so clearly indicated. 2 pi, though. 3 pi, 4 pi, 5 pi. So it looks like every multiple of pi. All right, so let's see if that agrees. A was the graph that we settled on. Yep, and x-intercept at pi 0. x-intercept at 2 pi 0, negative pi 0, negative 2 pi 0. Seems to hold up. Vortical asymptotes. How do you find the vortical asymptotes of a fraction like this? Think like rational functions. How do you find vortical asymptotes of rational functions? So a vortical asymptote is what happens when you divide by 0. As long as you don't also multiply by 0. So that means I need to see when the denominator is 0 to find vortical asymptotes. So let's set the denominator equal to 0 and see what we get. And this time I'll advocate using the graph of cosine instead. Because we could use the unit circle, but I just want to use the other mindset. There's a graph of cosine of x. What x values do you see that results in cosine being 0? So where on this graph do you see a y value of 0? I hear a pi over 2. There's a y value of 0. Any other places? 3 pi over 2. Looks like also negative those same things, which isn't surprising. Cosine is even. So it looks like odd multiples of pi divided by 2. All right, well, let's see. Yeah, that looks like pi over 2. 3 pi over 2, negative pi over 2, negative 3 pi over 2. I think that works out correctly. So here's what I'd like you to do for the remaining ones. And I'll break you all up, assign different people to different ones. Secant, cotangent, cosecant. Perform a similar analysis. And maybe I'll do this. Secant, cosecant. So perform all of these same analyses for those functions and see what options you settle on. Discuss things with each other if you would like. I thought you had a vortical asymptote. Oh, yeah. So notice some of these things don't have y-intercepts. So there's a good chance that whichever one I'm asking you to do might not have a y-intercept. Instead, it might have a vortical asymptote at x equals 0. over here. So y equal to secant of x. Does it have a y-intercept? What y-intercept did you get? I hear a y-intercept of 1. Do I hear a second? Do I hear a call to do? Okay, then I will not. Yeah, so it looks like the y-intercept is at 0, 1. And now let's take a look. Is that enough information you can actually pin down which graph that is? Which one? I guess I left. Nice. So that should be secant of x. And maybe we'll just read off one thing. So secant should be like 1 over cosine. So whenever cosine of is 0, secant should have a vertical asymptote. Cosine is 0 at pi over 2. Does this have a vertical asymptote at pi over 2? Nice. Did the other vertical asymptotes also line up correctly? And it looks like this has no x-intercepts. Is that correct? Yeah, right. The numerator is just 1. Secant is 1 over cosine. So, yeah. 1 is never 0. Cosecant. What did you get as far as y-intercepts go? Is that enough information to pin down which of these graphs it might be? Well, no. I mean, neither of these have a y-intercept, so maybe after one more fact you do. What's something else you can tell me? So either x-intercepts or vertical asymptotes. What's something else you can tell me about cosecant? How about x-intercepts? You can't tell me about them? There are none. Is that enough information to figure out which one? Which one? D, I think. This one has.
That one crosses it.
So I guess this one must be cotangent of x, which maybe I'll have you check on your intern. Yeah.
Can you talk about how you got this, like, no y-intercept for cotangent?
Yeah. For cosecant. Cotangent does. Hopefully I didn't say cotangent. I want to talk about cosecant. Let's find the x-intercepts of cosecant. Or do you want me to find the x-intercepts of cotangent? Okay, we'll do both. Well, let's talk about x-intercepts. So to find x-intercepts, you would set 1 over sine of x equals 0. But the only way a fraction can be 0 is if the numerator is 0. So for this to be equal to 0, 1 has to be equal to 0. For what x values is 1 equal to 0? 1 is not equal to 0. So that's why there are no x-intercepts. For cotangent, let's play the same game. To find the x-intercepts of... Oh, I wrote none in the wrong place. We were talking about cosecant. Let's find the x-intercepts of cotangent. Well, I guess you can look at the graph and see that cotangent also has no y-intercept. We haven't justified that. So let's see, it would be cosine x divided by sine x equals 0. What's the only way a fraction can be 0? Numerator is 0. And that's special about 0. Right? A fraction can be 5 without the numerator being 5. Right? You cross multiply and anything times 0 is 0. So that means that I'm in the situation where I want to see where is cosine of x equal to 0. And now we'll see what people think. Should we solve that equation by looking at the unit circle or the graph of cosine? Unit circle? Graph of cosine. Cool. Graph of cosine it is. There's the graph of cosine. Do you see an x value that results in cosine equals 0? I see a pi over 2. I also see negative pi over 2, also plus or minus 3 pi over 2. So this better have x-intercepts at every odd multiple of pi over 2. Pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. Yeah, that seems to have that. Cool. That feel pretty good? And so I'll give you a few problems as the class progresses and things like homeworks and exams, where you'll just have to remember what the graphs of sine, cosine, tangent, cotangent, secant, and cosecant, what they look like. But notice you don't really need to remember what they look like if you remember what sine and cosine do. You can reinvent that on the spot by like looking for particle asymptotes and stuff. That feel pretty good? Nice. With my remaining couple minutes, I have already updated the schedule, so like I'm behind what the schedule was, but not what the schedule is. Let's talk about what we will start in on next time. Maybe we'll make some progress. So all of the trig functions just have to do with stuff on the unit circle. The unit circle is extremely symmetric. Right? It has all the symmetries. If you put points over the line y equals x, you get the unit circle back. If you flip over the line y equals 0, same. If you flip over the origin, yeah, you still get points. Each of those symmetries will tell you something about trig functions. And maybe we'll start with the one that like corresponds to doing nothing. So let's suppose you add a multiple of 2 pi to an angle. Let's think about what that'll do to trig functions. What type of angle does 2 pi correspond to? All the way around the circle. So an angle of 2 pi k corresponds to k full times around the circle. So you can think of theta plus 2 pi k as first going around the circle by k full revolutions, and then an extra angle of theta. So let's think about that. So let's suppose I tell you to start at the point 1, 0 on the unit circle, walk 100 times around the circle, and then go forward by an extra angle of, I don't know, pi over 4. Do you have to do those 100 full revolutions to know what coordinates you'll land on at the end? No. You can just ignore them. So here's the first fact in here. You can ignore that plus 2 pi k. Cosine of theta plus 2 pi k is the same as the cosine of theta. And the same with all the other trig functions. So that's exactly what is going to happen in this next pack of notes. Adding 2 pi k plus theta corresponds to a full revolution plus theta. So cosine of 2 pi k plus theta is the same as cosine theta. Sine of 2 pi k plus theta is the same as sine of theta. What we'll do with the rest, in the rest of this note, is we'll use ideas like this to get a bunch of other symmetries. Yeah.
K is not a whole.
K has to be a whole number. If K is not a whole number, then there is a rule called angle addition that you can take advantage of. And I guess if K is like an odd multiple of pi over 2, then like we'll still get something, but it'll be not just nothing. And let's see, I don't think I updated the Canvas deadlines as of last weekend. So, I think when I get up to my office in the next hour, you are still set to get Canvas notifications. You'll get an email indicating that I pushed a deadline back.
Which deadline?
The stuff that we just finished today,
Okay.
because the previous deadline assumed that we had finished it on Friday.
Alright. Awesome.
I'm pretty sure it's just a web walkthrough, so like,
Yeah.
the deadline means something, but not a whole lot.
Thank you. Have a good rest of your day.
You too. There is an exam next week, yes. You're missing for like, you know the exams, right? Yeah. And it was for like, a reason that seemed excused if I remember correctly.
I can send you like
Oh yeah, we should do that. So, since it's excused, if you rather do it before the field trip, you could. That seems like maybe it would be all rush, but if you rather, we could do it on like Friday. The exam doesn't exist yet, I don't think. But we could also do it, so the exam itself is on Wednesday. So like, bonus day would also be fine. What day do you get back from Monday?
oh, it's on Wednesday. Okay, no, I always I'll get it on Wednesday.
Okay, double check that I'm not lying, because you seem quite confident. I think
Yeah.
that Monday is the review day.
Yeah, I got confused.
No, let's check, because I cannot be trusted to keep track of a schedule.
Will you be posting a review or I know it's on your
It will appear. There's this, symmetries. Yeah, right now Monday is review. Wednesday is the exam. Cool. All right, so, all right. Glad we tried. Looks like we'll be fine. I should stop the recording so I don't post a 2-hour video.